Okay, yeah. So good evening, everyone. So this session is for week 8. I hope you have started watching the lecture of week 8, and we have discussed the week 7 greedy part in the last week. Now this week is for the another techniques to design the algorithms. So that is actually divide and conquer approach. Okay, so today we will cover these concepts, so which is covered in the week 8, and there is one topic, recurrence relation. So that is also required because if we are just performing divide and conquer, so many of the algorithms we use the recursive solution for that. So because of that, we need to know that how to calculate the complexity for that such type of algorithm, which is based on the divide and conquer techniques. Okay, so we will discuss today divide and conquer technique. So before starting the session, if anyone have any query or anything to discuss, any specific. So next week you have quiz 2. Okay, and the syllabus for that quiz 2 is till week 8 and mainly from week 5 to week 8. Okay, so some topics are actually interrelated. That complexity topic, you know that that is comes in every week. So that we because of that we generally say that the syllabus is till week 8 for the quiz 2, but mainly the topics will be come from the week 5 to week 8 in this quiz 2 exam. Okay, yeah. So any specific query in week 8, if you have watched the video or if you have done the if you have seen the concepts, any topic. Okay, so then let's move from the topic wise. And if you have any doubt during the explanation, just ask me.
See that lecture on integer multiplication is a little complicated. If you can,
Yeah, that is actually little complicated because of that some mathematical formulation of that algorithm. So yeah, I'll try to cover that also. Okay. So yeah, we will discuss that how we are breaking the things and we are getting this some better solution. Okay. Okay. I hope my
So,
screen is visible.
which week
Yes.
are we doing today?
Week 8.
Okay.
Okay. Yeah. So I hope my screen is visible and let's open the week 8 content. So yeah, these are the topic we have in the week 8. So mainly the topic is divide and conquer, and this is the strategy to design the algorithm. And other are actually example of this concept. So we are just solving some problems using these techniques, and we are getting the solution, efficient solution. We can say that. Okay, we are getting the efficient solution for these algorithms. So now, first thing, divide and conquer. The meaning of this divide and conquer, you have already seen some algorithm in the previous weeks. Okay, I don't know you have noticed down this term. So this divide and conquer you have used in that. Yeah, please ask if anyone have raised the hand. I haven't. One second. Okay, nobody. Okay, one second. Yeah. So divide and conquer, you have already seen some algorithms. So these algorithms are quick sort and merge sort. You have seen in the week 2 and 3. So in these algorithm means divide and conquer means we are dividing the problem into sub problems. Okay, so we are dividing the problem into half and then another, then again half, and we are solving all these problems separately, and we are just getting the solution from each sub problem, and we are merging the solution and getting the final solution. Okay, so in this way we are so you can see that point, break up the problem into disjoint sub problems. So disjoint means that problems are not that sub problems are not interacting to each part. Okay, when we are solving the sub problems, so all these sub problems are separate, but after that we are combining the sub problem solution efficiently. So that is the way to solve the problem. So these are very common example. You have seen this merge sort, and merge sort we have break. You know that we have just a input list, unsorted list, and after that we are breaking that input list into two parts, then again two parts, and we are dividing this till when each element becomes separate, okay, at the last level. And at this way we know that if we are just dealing with single element, so we will consider that single element is a sorted element, okay, so there is no comparison with this. So single element is sorted element. So now we will start the merging process. So merging process, after dividing till this level, after we are starting the merging process. So merging process means we are merging two sorted array. Okay, so we are merging two sorted array, and that operation we can do in the linear time. Okay, if we have two sorted array like this, so if we have two sorted array, first is 1, 3, and 5, and then 6. Okay, another we have like this, so 2, 4, and 7 and 8, like this. Okay, so here both lists are sorted. We have the same size two list. So this list is also sorted, this is also sorted. Now we will merge these two sorted lists and we will get a final sorted list after combine this. So the final result will be like this. So 1, and then 2, then 3, then 4, then 5, then 6, then 7, then 8. Okay, so we will merge in this way. So these two sorted lists into one sorted list, and this operation we can easily perform in the linear time. So we can simply start the comparison from first element with the first element of the another list, and which element is smaller, that will move to the final list. Okay, and pointer will also move to the next element of the smaller element that side. So in this way we will compare each element one by one, and we will shift all element in the sorted order in the final list. So this process performed in the constant order of n time. And so that means we have started this process from the last level. So when the elements are single, now you will get the two elements which are actually sorted. Same for the another part. Okay, so you will get two elements in the sorted order. Again, okay, like this. Now again same things we will do. We will just merge two sorted list of the that we have got from the previous part. Okay, then again we will perform the sorted, that merging sorted. So in this way we will solve this problem, and this is called as a divide and conquer strategy to solve this type of problem. Same things we are also doing with the quick sort. So quick sort also happen. We are just selecting one pivot element from the list. We can select either first element or last element or any random middle element also. And after selecting the pivot element, we are performing one partition process, and we are just shifting all the elements in that way. So all elements which are smaller than the pivot element will move to the left side of the pivot. Okay, so that means so we will arrange our element in that way. So all smaller elements of the pivot element will come to the left, and all greater element of the pivot element will come to the right side, and pivot element will come at the correct position. Okay, so that means correct position means, so after sorting the list, what is the actual position of this pivot? That pivot will shift it to that position in the one process, that partition process. That left side all element will be smaller, right side all element will be greater than to this, but not guaranteed that all are actually in the sorted order. It may be in any order. And after getting the pivot position, so that means we got the one correct position for one element, and we have two parts now. Okay, now problem is divided into two parts. So this part we will again sort in the same way, and this part we will again sort in the same way, and both problems will be solved separately. Okay, and then again we will do the same things, and we will get another pivot. So this is like P1, and then you will get P2 for the second partition process. Same for this side. You will get left and right, and left and right side. This. So in this way you are dividing the one problem into a sub problems every time, and each sub problem is solving separately. So these are some very common example you have already seen before, and how we are getting the complexity for that. In general, we use the recursive solution of that type of problem. So merge sort, quick sort, we use the recursive solution. Okay, so in recursive solution, if we wanted to calculate the complexity of the recursive solution, so we should know that because we are calling the same process again and again, okay, that's calling the itself, that function. So we need to know how much time that call is actually happened. So we need to count that call. So this is the one thing. Another thing is, every time when we are entering into the function, what our function is taking the time apart from the recursive call. So that time is the another part. So that means if we can just write a relation for this, the time relation for that recursive solution, so we can represent like this. So Tn is the total time for n input. Okay, so initially we are considering that we have the n input, but after that, now we are in our recursive call, we have some recursive uh, in our recursive solution, we have some recursive call. So how many times we call recursively the same function, so that we will write here. So that means, suppose for merge sort and quick sort, if we are writing the that recurrence relation, so in these algorithms we call 2 times, okay, in merge sort in all cases, and merge that quick sort in best and average cases, not worst case. Okay, so now suppose we are calling 2 times our same function recursively from the main, say that function. Okay, so we will write 2 times this Tn. Okay, and what size we are passing to the next call, that we will write here. So like this. Okay, so this part is actually representing the recursive calls, how many times we are calling the same function again, and what size we are passing to the next call. So this is just for counting the call. Okay, so because of that, we have written the time actually T. That means we will calculate the time for this part separately. And apart from this call, whatever for function that is time taking for other operations. Okay, so that time we will write as a additional time plus. Okay, so in merge sort, you know that we are performing merge operation, so that operation takes order of n time. So we can write like order of n here. And same in the quick sort, that partition process take order of n time. Okay, so because of that, we also write the same order of n for quick sort also, in best case and average case. So this is the meaning of this recurrence relation. Okay, so we generally write this recurrence relation for recursive solution. So now we are learning this, we are looking this divide and conquer algorithms strategy in more depth, and we are just discussing some new example. Okay, so first is, these are the examples. Okay, so where we can use this divide and conquer approach, and we can improve the efficiency. So we will come at this recurrence relation at the later. So how we can solve this recurrence relation using some methods to calculate the complexity. So that we will discuss at the last. Okay, so that last topic, recursion tree. Now the first example is discuss this counting inversion. Okay, so this is one problem which is actually common. This is very related to the common real life scenario. Okay, so here professor have discussed some example like that comparing the rankings.
Sir, just
Yes.
one small interruption.
Hmm.
So far what we have studied earlier, from that merge sort and quick sorts are example of divide and conquer.
Yes. Okay, and also this binary search you have learned, that binary search algorithm. So that is also an example of divide and conquer, but not exactly divide and conquer. That is called as a divide and decrease. Okay, but
Divide.
sometimes we also consider that binary search, that type of problems, into this category, divide and conquer, because where we are also dividing the problem, that dividing, but at that type of problems we are decreasing the problem size. Okay, here we are not decreasing the size, we are just dividing the problem and solving each subproblem separately. But divide and decrease means we are dividing the problem, but we are removing some part of the problem in every time when we are dividing. Okay, so because of that, is called as a divide and decrease. So that binary search type of problems comes under that category, but some place you will find out that will also consider as a divide and conquer.
Okay,
Okay,
sir. Yeah.
yeah, so but concur means actually we will merge the solution of the sub problems, but in binary search type of problems we are not merging the solution, actually we are just removing the half part of the problems for the next process. So because of that, we generally say that divide and decrease that process. Okay. So yeah, so this is the first problem, counting inversion, and some real life examples are there. So this comparing the rankings actually, and there are very common use you can see in your real life. So like if you search, suppose if you are looking Google News, and if you search any specific type of news in the Google, so like if you are searching some gaming type of application or some specific data science or related some news, if you are searching, then after that you will get a related data science related news. You will get a more news related to the data science if you have searched one time. Okay, so same things that Netflix or these that OTTs are actually also follows these things. So if you are giving some ranking or that rating to some that movies or something, so they also record your preference actually. They also record your preference, so what type of that content you are actually liking, and that that actually that your that ratings actually they used for the others peoples. So if suppose if someone is actually also searching or giving the rating or looking like you, so they actually match that 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 person rating is similar to which another person. Okay, so based on that, they actually just suggest some content which you can like. So that actually happens by this type of algorithm, that inversion pair. So this example is given here. So identify people who share your likes and dislikes. So they just find out that what are the difference actually between your ranking and another person ranking, and based on that they decide that your that preference is similar to which another person's, and based on that they just suggest some content what you are searching. So here this example is given, like suppose if you have given some ranking, this is the A person and this is the B person. Okay, and you have just given this ranking to some movies. Suppose if have some 5 movies and you have just giving this ranking, so 1 2 3 4 5. Okay, so another person have given this different ranking for these movies. So that means he's giving the first preference of the second movie, then another second preference for the fourth movie, like this. Okay, so what is the difference between this A ranking, and what is the that in between the A and B ranking? So what is the difference? So how we can find out this difference? So there is one method. This is called as a inversion in pairs. Okay, and based on that we can figure out that if this inversion pair counting is less, so that means ranking is more similar. If this count of inversion pair is high, then that ranking is not similar. So this is very common. So suppose if you have the both A and B are giving the same ranking, so 1 2 3 4 5, so there is no inversion pair actually. So let's see what is the inversion pair according to the definition. So we will compare this B with respect to this A. Okay, so we want to find out the inversion pair of B with respect to A.
Sir, for this example, on the top of this, let's say we write 5 movie names, okay? So person A has ranked those movies as 1, 2, like that. And then, but from this, what we interpret actually?
So actually you have 5 movie. So A is actually giving the first that suppose this is the name of the movie, 1 2 3 4 5, and these are the position actually. So this is the first position, this is the first, this is the second position, this is the third position, this is fourth position, this is fifth position. So this is the written here. So same for the B actually, this first 2 3 4, this 5 position. A is just putting the first movie, this M1 at the first place. Okay, M2 at the second place, M3 as the third place, M4 as the fifth place, M5 as the M4 is the fourth place, M5 is the fifth place. But B is giving ranking like this, so B is giving M2 as the first place. So that means B is liking this is the most nice movie.
Yeah, fine. But both of them are giving same rating for movie 3.
Huh.
So with that data, we are saying that both of them liking the movie 3, but what
Yes.
else we know from this actually?
So first things we will put this ranking. So this is M4, this is M3, this is M1, and this is M also this is M5. Okay. So first we will find out that how much this B ranking is similar to this A ranking. Okay. If this is more similar, then we can give the preference to the A based on that. Suppose if so what actually A is liking. So if this ranking is both A and B is too much similar, then what A is actually liking other movie apart from this, then we can suggest that movie to the B also. Okay, because interest of A and B is looking similar. So based on the interest, we can suggest some movies to the A which actually likes by the B.
Okay, so let's say
Okay.
they 5 movies they have watched, and
Hmm.
some more movies are watched by person A, but B
Yes.
is not watching any further movies.
Yeah, so that
Suggestion.
they can suggest that maybe you will like that.
Okay.
Yeah, so that similarity actually we are finding out this inversion pair, this type of algorithms. So that inversion pair means, so we are assuming that this is the first A preference, so this is in the sorted order exactly 1 2 3 4 5, and this is another preference that ranking is given. So we will find out that what is the inversion pair value for this corresponding to this sorted order. Okay, A, we are assuming that. So like here, so how we can find out that? So the definition of inversion pair is the pair I comma j, okay, from the same that ranking, okay, where I is less than j, but j appears before I. Okay, the value of I is less than j, but j appears before I. That means big value is coming before the smaller value in this case. So here, if you think that this 2 4 3 1 5, okay, now we want to find out the inversion pair corresponding to this sorted sequence. So 1 2 3 4 5. So that means the value should be come in this order. So that means this is this is smaller than to the second is smaller than to the third, like this. Okay, but here what is happening, this if you just find out that this first value and find out the pair corresponding for this. So you can see 2, then 4. So in the sorted order, 4 is coming after the 2. So this is fine. So 2 and 4 is fine. 2 and 3, this is also fine because you can see 3 is coming after the 2. So this is the same here. So 2 is coming, the 3 is coming after the 2. But here 2 and 1, if you see this, here order is reverse. Okay, in the above process, you can see 1 is coming before 2, but here 2 is coming before 1. So this is one inversion pair actually. We can note down this. This 2 and 1 is the one inversion pair. And same things 2 and 5. Yeah, this is in the correct or sorted order. So 5 is greater and coming after that. Same we can check for 4. So 4 and 3. You can see 3 is smaller but coming after that. So that this is a inversion pair. So 4 and 3. This is the one. 4 and 1. This is also incorrect. The bigger value is coming before the smaller value. So again, this is 4 comma 1 is also a one inversion pair. So now 4 and 5, this is in the correct order. So 5 is greater and it is coming after that 4. So this is fine. Now 3 and 1. So you can see 3 or 1. This is also not in the correct order. So 3 comma 1. This is also a one inversion pair. And 3 5. This is also correct. And 1 and 5. This is also correct. So now you find out that these are the inversion pair in this order 2 4 3 1 5 corresponding to this sorted order. Okay, so 1 2 3 4 5. So we can figure out that what is the inversion count value. If this inversion count value is less, so that means our ranking is more similar. If this inversion count is high, that means our ranking is different. So what is the maximum and minimum value possible for the that inversion count? So this is also one important question for the exam. So what is the minimum possible inversion pair is if we have this, and we are assuming that we will compare this our inversion pair with respect to the sorted order. Okay, so if we are given like this 1 2 3 4 5, okay, and corresponding to the sorted order, this is also in the sorted order, so that means there is no inversion count is there in this ranking. Okay, so that means minimum is possible zero inversion count. What is the maximum? So here maximum, you can use the formula, so that what is the maximum if this is given in the reverse order, so like this, so 5 4 3 2 1. Okay, and you want to just compare with this into the sorted order, so 1 2 3 4 5 like this with respect to this. So here 5, for 5 you will get 4 inversion pair. Okay, so 4 for this 5. Then for 4 you will get 1 2 3, so plus 3. Then for 3 you will get 2. Okay, so 2 inversion pair, and for 2 you will get 1, so then 1. Okay, so that means 4 plus 3 7 plus 2 and total 10. For 5 value you are getting 10. So that means what formula you can directly use. So here n equal to 5, and answer you are getting maximum 10. This is the maximum value possible for inversion pair for 5 value. So here we can also use one formula, so that is actually n 5 into n minus 1 divided by 2. Okay, and you can just use this, so 5 into 4 divided by 2, and you are getting the same 10. So this formula you can note down, and you can use this directly. Sometimes if it is asked that if you have that n equal to 10 distinct value, and just what is the maximum that inversion count for that. Okay, so you can directly put this formula. And what is the minimum? Minimum is 0 for that. Now this is the separate story regarding the what is inversion pair, what is the minimum and maximum things. And now the question is how we can find out this inversion count. So I have discussed one method. What we can do, we can compare one by one. So like this, we are comparing in the example. So 5 4 3 2 1. If we are giving this sequence, so what we are doing, we are picking one number and we are traversing all the numbers. Okay, if we are finding any number which is smaller than this, we will just count one inversion pair after this. Okay, so we are traversing completely. After we will pick second element, and then we will traverse the remaining element. If we are getting less element, then we will increment our count. So in this way, what type of solution we are getting? Similar to your selection sort or insertion sort. That means first time we are traversing n element, next time we are traversing n minus 1 element, now n minus 2 element, like this. Okay, till 1. So that means if you add all these steps, you will get a complexity big of n square. Okay, n into n plus 1 divided by 2. Okay, and when you multiply this n into n, and you will get n square complexity. Okay,
So how did you get 10 here?
a 10 here. Okay, so you can see, just note down what are the inversion pair with respect to 5. So this 4 is smaller, 3 is smaller. So what value which are coming after that and which is smaller than this, so that will be considered as one inversion pair. So 5 comma 4. So 5 comma 3, 5 comma 2, 5 comma 1. Okay, all these are the inversion pair with respect to 5. Same, then 4 comma 3, 4 comma 2, 4 comma 1. So these are the 3. Now 3 comma 2, 3 comma 1. Okay, and last is 2 comma 1. So these are actually total 10 inversion pair you are finding out, and this is the maximum number if our list is correct, completely reverse sorted. Okay, and that value you can directly calculate by this formula. If n is given equal to 5, so you can calculate, so 5 into 5 minus 1, that divided by 2. Okay, so you can directly calculate 10x total number of count inversion pair. Okay, so this is the one thing. So this is the problem. We wanted to compare this ranking. We want to count this inversion pair, and how we can count this. So this is the naive approach which I am just trying to do here. So I am just taking one element and comparing each remaining elements. Okay, and then figuring out that. So in this way, you are getting this steps. So first iteration, I am getting n steps. Second iteration, I am getting n minus 1, then n minus 2, and till 1, last one. And when we add all these, you will get a n into n plus 1 divided by 2. Okay, when you add this series. So if you multiply this, n square by 2 and plus n by 2. Okay, and that means higher term is n square. So overall complexity will become n square. So now this is the naive approach solution. So that means if you are solving this problem, if you wanted to count this inversion pair, you need this complexity. Your algorithm will take this order of n square complexity if you are following this approach. But now the question is how we can improve this. Can we figure out this inversion count in less time in less that efficient by the efficient code? So the solution for this is covered by this merge sort algorithm. If you have already seen this merge sort algorithm, now we are following the same algorithm, and during the merge process we are counting this inversion count. Okay, so this merge and count, this is the same step. Okay, similar to your merge step. Okay, in the merge sort, but we have given the name here merge and count. So because we are also merging and we are also counting the inversion pair, pair by this process. But how we are achieving this time, that n log n? So you know that this algorithm takes n log n time. Okay, merge sort takes n log n time. So by the help of this merge sort, we will also figure out this count information in the same time. So how we can do this? So here what we will do, suppose if you have two sorted list, that first left A list and then B list. Okay, and you have some element, like you have some 5 element in this and 5 element in this. Okay, I'm writing some element like 1, 3, 5, 8, 10. Okay, and this side 2, 4, 6. Here we will, because he will consider this time, we will consider all unique element. Okay, so because in general for the ranking we consider as a distinct element, so we will take some different elements, so like 7 and 12. Okay, now we have this type of two sorted list, and we are merging these list by the merge process. Okay, so in this way, you know that when we are merging the elements, so elements will come into the sorted order, and our merging happens like this. We have first list and we have the second list, and I'm writing in vertically now, so to represent 1, 3, 5, 8 and 10. And here also we have this 2, 4, 6 and 7 and 12. Okay, so how merging happens? We take some I pointer here and j pointer here at this indexing, because both are arrays. So 0, 1, 2, 3, 4 and 0, 1, 2, 3, 4. And then we start comparisons, and we have the final list, and we so this I, that A ith element and that B jth element, we will compare which one is the smaller. We will move that element to the final list, and we will move the pointer of that. Okay, so in this way, when we are comparing 1 and 2, okay, so this 1 is smaller than this 2, that this A will be this first element will be moved here. So in this process, when we are doing this process, so if our AI element, so this AI element is less than BJ element, so we no need to do anything. So okay, so we will just perform the process, and we will know. So that means AI. So because our merge sort algorithm divide like this, so this part is coming. We perform the, so yeah, this part is coming before the second part when we are merging. Okay, so A part, if the element of A is smaller than element of B, so that means elements are coming in the correct order. So that means this left side element is smaller to the right side element. So this is one. So that means this is in the correct order, not in the reverse order. Okay, so we will not check anything. So we will simply perform our merging, so that we will shift our element to here and like this. Okay, but in the another case, so yeah, regarding this second element, so after shifting this first element, just move next to this I equal to 1. And what we found here, Here what we are looking at, B. So this B element, J element, this 2 is smaller than this 3. Okay. So what we can conclude from here, so that means this 2 is smaller than 3. So that means this is one that reverse, actually inversion pair. So 3 is coming before and 2 is coming after that. So this is one inversion pair. So 3 and 2. Now we figure out that, so that means at any point, if you are getting AI is greater than BJ. Okay. So this is the condition for inversion pair for this. But so this is one inversion pair, but we can conclude all the inversion pair which are coming after. So we are actually getting from this 2. We can directly conclude. How we can conclude that? Because if this 2 is smaller than this 3, okay, if this 2 is smaller than 3, definitely it will also be smaller than the remaining element of this first list. Okay, because this list is in sorting order. Okay, if this 2 is smaller than 3, so all elements are coming after that, after this 3 will also be greater than this 2. So that means this 2 will also make inversion with all remaining element after 3 in this A list. So what size we have for A? So we have 5 element, and what is the point? We have I at this time. Okay, so this is 1. I is representing to 1 index. We can directly figure out that if we are getting this condition, AI is greater than BJ. So we can directly figure out that 5, what is the size of this A, minus I index. What is the current I index? Okay, so I index is 1. So 5 minus 1. And that means 4. We can directly increment our inversion count 4 by getting this condition. Okay, and we will shift our the 2 here. So this 2 will come here, but at this time we will directly computing all the count, that inversion count, which are actually creating with this 2 by this formula. So just size of this array, left array, minus what is the current index I. So it will calculate all the remaining elements, including this 3. So 3, 5, 8, 10. So that means this 2 will create an inversion pair with all elements, remaining element of this set. So we will directly increment this.
Sorry, sir, can you repeat that once again?
Okay.
This 5 minus 1.
Okay, so here we have 2 lists. So I'm just creating again. So this A list and this B, and here we have the element like 1, 3, 5, or let me check. So 1, 3, 5, 8, 10, 1, 3, 5, 8, 10. Okay, and this side we have 2 and that 4, 6, 7, 12. So 4, 6, 7, 12. And this is actually both are the list. So 0 indexing 1, 2, 3, 4. And this is also 0, 1, 2, 3, 4. So we start comparison one by one. So I is pointing to this and J is pointing to this element. Okay. If we are getting this condition, A of I index, okay, is less than B of J. So that means if element of AI is lesser than BJ, so that means these pair is actually in the correct order. So A is the left side of the array and B is the right side of the array. So if Ath element is the smaller to the Bth element, so that means that order of the elements are correct. So 1 is smaller than to the 2. Okay. So and now A is in the left. So this 1 is coming on the left side and the 2 is coming on the right side in the array. So this order is correct. So no need to count this as a inversion count. But if at any point, if you are getting AI is greater than BJ, so this is the condition for inversion count. So element which are coming in the A is greater than to the element of the B. So that means this pair is actually creating a inversion pair, reverse order, not in the sorted order. So if you are getting this condition true at any comparison during the merging process, so we can also conclude all the remaining that inversion count of for that element. So here this first 1 and 2, when we are comparing this is in the correct order. So we have shifted 1 here. Now we shifted our I to next elements, this element. Now we will start comparison again. Okay, so that means 3 and 2. We will compare 3 and 2, which one is the smaller. Now we find out that this B element is smaller. This B1 is this 2 element is smaller than of this AI. So now we got this true condition. So, and this is creating an inversion pair. Okay, so this is creating an inversion pair, and that means one inversion count we found. But we can also conclude all the remaining inversion pair with respect to this two element in the B. How we can do this? So because we know that A list is in the sorted order. If this 2 is smaller than this 3, so this 2 will also be smaller than all the remaining element, because all are greater than this 3 after this. Okay, so how many elements we are getting? So this is one we found during the comparison, but remaining elements we will also count by the size of this array. Okay, so what is the size of this array is 5. Okay, length of this array minus what is the current index, because index is started from 0, so we are getting this 1. So 5 minus 1, and 5 minus 1 is we are getting 4. 4 means we have 4 elements, 3, 5, 8, 10, which are actually greater than this 2 and coming before that in A. So all are creating the inversion count with this 2. So we will directly increment our inversion count by this 4 value when we are getting this condition. Okay, no need to compare with all. Okay, so we are not comparing this 2 with 3, 2 with 4, 5, 2 with 8, 2 with 10. We are not doing this process. We are simply comparing with this 2 with 3. And after getting this condition true, we are directly incrementing our count by 4. Okay, or what are the remaining elements we have? So this is a constant operation we are performing. That means in the merging operation, we are not increasing our complexity for this process. We are only doing this constant operation. So our merge process will only remain or that linear time, that order of n. So now if you can see the algorithm for this, where we are doing this. So you can see this merge process, and this is the merge process. And in this merge process, we have the length of A part. This is A list and this is the B list. Okay, A, M for the A and N for the B. And now you can see we are maintaining this count. This count is for inversion count. This is initialized with 0. Okay, and after that we are performing merge process. So this is the merge process. If our K is less than equal to M plus N, then we are doing this process. If our I is reached at the last index, okay, so that means if our I is completely full, this is not a last index, this is the that means size of the A. So that means we have the last index from 0 to M minus 1. And if after comparison, if our I is reached at the M point, so that means out of the index. So this is the identification of that that A list is completed. Okay, A list is completed for the comparison. Now some elements are remaining in the B. So that elements actually we will directly include our final list. So this is the merging process, that merge sort process. This is nothing new. Okay, and if our J, that means our B list is completed. So this completed means what actually? So what happens sometimes? So this is okay. So this side. So suppose our A list have this type 1, 2, 3, 4, right? Okay, and our B list have 5, 6, 7, 8. Okay, and we are merging these two. So what will happen? Our I will point to this and J will point to this. Now we will figure out that I is smaller. So 1 will move to the final list. Now I will increment. Okay, so now 2 is smaller than this 5. Then 2 will move. Then 3 I will move here. Okay, so 3 will move here, and then I will move to the 4, this value. Now 4 will move here. Now I will move one more. Okay, so this is the last, that length of the list. So that means all elements are completed of A. Now anything is remaining in the B, we will directly move this here in the same order, 5, 6, 7, 8. So this process is actually handling this info things. If by the first, if elements of the A list is completed, then we will shift our all remaining B element into our final list, C dot of N. Okay, and same things, if our elements of B list is completed, then we will shift our all remaining element of A directly into C. And now this is the condition when we have the element in both lists. So if our AI is less than bj, so as I mentioned that if our AI is smaller than bj, so we will do the simple merging process. We will append this AI to the final list and we will increment I and k. K is pointing to the final resultant list pointer. Okay, so nothing doing. But else part. So this is the else part for this. That when AI is greater than the bj. Okay, here all elements are distinct, so you will not get a equal condition. So if AI is greater than bj, so this is covering by else part. And here you can see we are shifting our smaller element to the final list. We are shifting this j pointer 1, k pointer 1, and here we are, you can see we are directly incrementing our count value by m minus 1. So m is representing the size of that a and minus I. So you will directly increment how you will directly get this information that how many counter inversion, the count inversion count you are getting from this bj with respect to bj value. You are directly incrementing this information in the one step, constant step. You are not traversing, you are not comparing with the all elements. So by only this modification, we are also getting the count information, and we are not changing anything in our process. All remaining processes are actually exact merge sort. And this count, we are getting this count from every recursive call. So because of that, we are getting this count information from every recursive call, and we are reading this. And finally, we are adding this, what count we are getting from every recursive call. And you will get the total inversion pair for the algorithm from the algorithm. Okay. So this is actually an inversion pair algorithm. So that means by the same process, merging merge sort process, we are getting this information how many inversion pair we have. Okay, with respect to sorted list. So here this input is given like this 2, 4, 3, 1, 5. So this we are passing to this merge sort, and you will get an inversion pair for this value. Okay, so this is a inversion pair algorithm. So how we are getting this information. So I hope this is clear. If you have any doubt, please ask.
Sir, clear this merge short and quick short. Even this BST, understand that it is related to divide and conquer this algorithm, and this inversion is byproduct of that. But how it is correlated to the divide and conquer actually?
So here we are using the merge sort, no?
Yeah, we are using
merge sort is an example of divide and conquer.
correct, but why we are interested in this inversion counter?
Yeah, as I mentioned that no, there are so many applications related to this. Previously, as I mentioned that many applications like this OTT service, these are actually, if you are searching any movie, okay, so you will also get some suggestion corresponding to that movie. That means your interest is actually matched with some another person. When you are just searching any movie, your interest actually that they calculate actually your interest with another person matching actually what you are searching. So how in the same rating, if any another person is also searching the same content, so based on that, what that person looking another things, that will be suggest to you.
Sir, that so the inversion count in total inversion encountered, if it is less or zero, that means
Yeah,
both the
more
person.
similar. Yeah, more similarity in the interest. Okay, so that means here we are counting the inversion pair, but that value is we are using some applications. So if this count inversion count is just representing the similarity or more that less similarity or more similarity, this count value. If this is less, that means your that value is more similar. Okay, so 0 means exact similar. If you have inversion count value 0, that means you have the exact similar with the sorted count. Yeah, please, someone have raised the hand, I think.
Sir, in this we just compared with two persons, A and B, and with same number of like, uh, they both have same length. But
Yes.
what if it is different lengths and there are more people? So how will this function work?
No, so here actually this perform with the everyone. So suppose if you have 5 persons, so A, B, C, D, E like this, okay. So that means if A is looking something, so that A interest will compare with B, then C, then D, then E. Okay, and which one is getting the less similar? More similarity. Suppose A is more similar to this D out of these all. So that means you will get the same suggestion which are actually searched by this D. Okay. So this inversion that count that algorithm runs with every pair. Okay, so that will found that closest, that more similar things, more similar that rating, and after that you will get the suggestion according to that similar one person. Okay, so there are some algorithms that this is not the exact algorithm they use. They use some modification version. So this is the basic idea behind that. Okay, so they use some advanced version. They use this concept to finding out the suggestions for the others. So, and this is a common example. You can just search any movie in the Prime or any OTT. You will also get some suggestion. Okay, so how they are actually giving that suggestion to you? They are doing some process behind that. They are not just giving randomly. So if you are interested in action movie, so that means they will just figure out that your interest, that which is similar to the other person and what that person is looking at. Based on that you
Sir,
will get.
is there any logic to have the minimum data set? So if the later person have not watched many movies, only very few,
So they actually, as I said, that this is the basic idea.
Oh, okay.
They use some modifications, so maybe they filtered the interest which are actually more similar to you. So suppose they are just looking that what rating you have given for some movie, and based on that they filter only that type of users and compare with them. So that is another thing. So that another higher algorithms actually used for the final things. But this is the basic idea behind that. So how the similarity actually calculated between two different ratings. Okay. So another things is we have just compared this with the sorted things. Otherwise, what happens to you have given two different rating like A and B. So suppose a rating is given for 5 movie is 3, 1, 5, 2, 4. Okay, and B's rating is given like that 5, 1, 3, 2, 4. Okay, here and you want to find it out the similarity of B with respect to A. So in this case, how you will calculate? Because we cannot apply this merge sort directly here, because here our corresponding sequence is not sorted, and our merge sort output is actually sorted. So what we can do, we can just mapping. Actually, we can apply the mapping corresponding for this. Okay, so what we can do, we can just place 1, 2, 3, 4, 5. Okay, and we can just put this sequence at this place. So that means 3, that 1, and that 5, and this is 2, and this is 4. Okay, so now we are just mapping this way. So we are assuming this sorted sequence, and corresponding we have this value. Now we will also figure out the sequence for B based on this mapping. Okay, so that means when we are writing this 5, so what is the corresponding 5 value we have? So based on that, we will figure out that. One second. So yeah, this is the corresponding sorted sequence. So like 1, 2, 3, 4, 5, and okay, so 5 is every 4. So yeah, so this mapping actually we have arranged that this is the sorted sequence, and when we will write this sequence for B, so we will check the mapping from this sequence. Okay, so what value we have written for this 5, so that will come at the first place. So 5 will come, and here it will be written as 4. Okay, so this value, and 1 mapping will be come here 3. So this sequence will be changed corresponding to this mapping. After that, we will apply the same process, and that will be checked with this corresponding sorted sequence. Okay, in this way. So you can calculate the difference. Okay, so you can just give the mapping for each number. So 3 to you are giving one name, for 1 you are giving 2, for 5 you are giving 3, like this, and after that you can apply this mapping. So I have mentioned the reverse thing, so order will be given like this. So 5, that means you will look from this side. So 5 we have mentioned 3, so this 3 will come at the corresponding here. Okay, and then 1 corresponding is 2, 2 value will come here. So in this way you will get the similar. So 3 corresponding 3 value is 1, so you will get 1, and the next 2 corresponding value is 4, so 4, and that you will get 4, then 4 corresponding is 5. So you can see we have got the new sequence. So that is 1 2 3 4 5, and here this is 3 2 1 and 4 5. So you can see we are getting the similar. So you can see similar value here, similar value here. So again you are getting similar one here. Okay, but now sequence is changed corresponding to the sorted sequence, and we will figure out that what is the inversion count for this. Okay, we will apply the same algorithm and you will figure out that what is the similarity in these two sequences. So in this way you can just compare any sequence, any that similarity with any sequence. Okay, yeah, so this is the first algorithm, and in this way you will get this information in the with the complexity big O order of L log n. So here nothing is new. We are using the merge sort algorithm. Only we are just using that count information. We are calculating that count information is merge process. If that smartly actually. Okay. So this is fine. Any query in this? No query, then let's move to the next. Okay, so this integer multiplication, this is a little bit that mathematically actually. So in general, when we perform any multiplications, so like if you are performing any multiplication 1 2 3 4 and 2 3 5 4, so like if you have 2 digit like this one and this one, so you perform this multiplication like 4 into 4, this type of, you take one value and you multiply with the all remaining value and just put that value here. After that you take one value and then multiply the remaining value, you put that here. So then next is that you will put here, that 2 that you will put here. Okay, and then after that you will perform sum all, and then you will get the multiplication. So that means the if you have the length n, okay, so suppose this length of the one element is n and another is also n, so you are getting complexity n square for this process. Okay, so here this there are some traditional method that we are following here for the multiplication is order of n square. Some improved method is also given, but still we are getting the order of n square by that method. After that, this is the final method which is discussed in the lecture, this Karatsuba algorithms. By that algorithm, we are getting better complexity. So this is not the correct one. Actually, I think some representation issue is there. So that is the different. Let's me open. Inversion count. Select. Let's me open one second. Yeah, this one. Okay, so if the final Karatsuba complexity we have different, so that is actually thing. Yeah, this one. This complexity we are getting. So you can see in Karatsuba algorithm we are getting this complexity n to the power 1.59, this one, which is lesser than to this n square. So using this divide and conquer approach, we are getting this complexity. And in algorithms, if you see the algorithms for this, what we are doing actually, Okay, so some naive approach method is discussed first. Let's move to that. Yeah, this is the Kasua. I am just explaining from my summary. So that algorithm is written in the better way. Yeah, this way. So here what we are doing, we are just multiplying this fast multiply by this method. So 3, 4, this is the size of the element. So 3, 4, 5, 6, and this element. And this is the size. Okay, these are the two value and x and y, and this is the size for that means we have the 4-digit number for each value. So here, if we are getting this x and y and n, okay, n is representing the size of the number. So if we are getting the size 1, so we will directly return the multiplication of x and y. Okay, so if the size is 1, so that means we are getting like 2 and 4 and 1. We will directly return the value 2 into 1. So this is a constant operation of the one with the 1 digit. Otherwise, what we will do, we will follow this process. So here we are dividing this number into 2 halves, and that means how we are dividing. So this is the part, that means we are dividing the half size. Suppose we have 4, then we will divide this number into 2 parts, and this m value is representing this n by 2, and you will get a integer value. So that for 2, so in that case, this 4 line, what it is representing, that first half of the that x value, and this is the second half. Okay, so we are just getting the floor division. So you will get a that suppose if you are getting this 3, 4, 5, 6. Okay, and this m is representing now 2. So this is that means 10 to the power 2. So this is 100. So you are dividing this value by 100. And what is the floor division? Okay, so what value here you will get? Only this value, 34. Okay, so 34 you will get for this 34, and after that reminder, this is the next operation is reminder. So 3, 4, 5, 6, and that reminder, okay, slash 100. So you will get the remaining part, 56. So what we are doing, we are simply dividing this 4-digit value into 2-digit value. Okay, so 34 and then 56. Same things we are doing with the right value, that y value. So y value is again divided by this, so this 8, 9. So that first part will be divided into 8, 9 and 0, 2. Okay, so we are breaking the problems of n size into the smaller size. So this is the again dividing process, and here we are performing some constant operation, a equal to xh plus xl. So that means xh, we are just adding this 34 and 56. Why we are doing this? Because we have this final formula and we need the value for that. Okay, so this is just example of some proof mathematically that if you are performing the calculation like this, you will get a final correct solution. So here we are just dividing all the value in this way. So we are getting this a value, b values by some constant operation, and here these are the 3 recursive call here. Okay, for the same that we are calling the same fast multiply. You can see first p equal to this is performing with the xh and ys. So that means this first half. So 3, 4, 5, 6, and next value is 8, 9, 0, 2. So that means we are calling the same algorithm with this size. Okay, so we are passing 3, 4, 8, 9, and size 2 in this call. Okay, so this is now a new call of the half size. Now this is the another call. Okay, so then we will again pass this xl, yl, and m. So that means this value, and 2 size. M is representing the half size of the. These are 2 recursive call, and another recursive call we are calling in the same way. Here we are passing this a and b. So that means after getting this half part, 34 plus 56, that is the a value, 89 plus 02, that is this b value, and then we are passing this with the same size. So that means the sum of this 34 plus 56, that is a, and then this is the b, and you will also that. Okay, so this is we will perform that this sum operation, and then you will pass again this r. This is also one same recursive call. After getting this p, q, or this information, you are using this in on that values in this final formula. Okay, so which is defined by this Karasuba. So you can just pass this p value into 10 to the power n. N is the initial 4 size. Okay, now this is the simple subtraction value, and this is again some division. That's all. Okay, so in this way, your problem is again divided into three part like this. So you are performing with the n. Okay, so now this problem is divided into three parts. So three, and each time we are reducing the size half. So we can say that we are dividing like this. So t n by 2, t n by 2, and t n by 2. Okay, initially this the size was n, but next time we are calling the same recursive function 3 times, and size is n by 2, n by 2, n by 2. Again, this will call 3 times. Okay, so you will get something here. But what will be the how many levels you will that you will complete this part? Okay, so you are dividing the problem into the half every time. So that means you will reach at the last level t1 in log n steps. Okay, log n steps you will reach at the last level. Now the complexity, what will be the complexity of this? So here it will not be the n log n, or this is like log n things, because here this times we are calling 3 times. So this recurrence relation will work like as a tn equal to 3t n by 2. Okay, and plus the additional work. So what is this additional work is required for that? So let's discuss that. That will be the constant, I think. So 1 second. Yeah, no, this is n actually. So n is for what? Okay, so
that four at the calling time, that is when I wanted to ask.
No, this is the 3 times. So that we have written 3t n by 2. But this n time we are taking for another calculation. So that is, I think, for this addition time. Okay, so we here we have 2-digit number and 2-digit number. Then we are adding this number. So you will get, if you are adding 2-digit number. Okay, so that m size that you have m element. Okay, so you have to perform addition. So like here this 34 plus 56. So that means you are performing addition with 2 plus 6, you will get something, and some remainder something. So after you will get a that n by 2 plus n by 2 size, you will get near close to your n size for this type of operation. So because of that, apart from this recursive call, you have the remaining time n constant this. Okay, so we are getting this recurrence relation. When we solve this recurrence relation, we will get this complexity that n to the power 1.5 something.
So that question here.
Mm-hmm.
So that addition you're doing, right? 34 plus 56. So that also we are actually doing log n number of times, right? Because you are going into this loop log n number of times iteration. So that addition also more accurate would be log n, correct?
No, actually, what happened here? So we will understand this calculation by the recursion tree. So here we will calculate the steps at each level. Okay. So what means we have this. This is the first step of the algorithm when problem is divided first time. So we are performing n option because our input size is n here. So we are performing this n operation additionally apart from the recursive call. Now we have 3 recursive call at this stage. So here our input size is n by 2. So that means our operation will also be n by 2. If you have n operation at the for input n. Same for here also n by 2 operation we will perform because input size is less. Same here n by 2 operation we have. But when we will add all the inputs operation at this level, so you will add 3 into n by 2, correct? So you will get this value at the next level. That means at the first level, when our input size was n, we are performing some operation with complexity order of n, or number of operation, we can see that n. But here our input size is different for the each call. So our number of operation is also related to that. So n by 2 here, n by 2 here, n by 2 here. So we will add all these and we will get 3n by 2. And now our total, so here we are getting different operation at each level. So here n, here 3n by 2. Next level you will get a 9n by 2. Okay, so because you have total 9 call, or n by, your size will become n by 4. So you will get a n, that 9n by 4. Yeah, this.
Okay.
Okay, so that means our number of operations are increasing. Our number of operations are increasing at each level, and we have log n levels total. Okay, because we are dividing the problem into half at each level. So you will reach into the log n steps. So if we are getting this type of sequence, then how we calculate the complexity? Because we have seen this for the merge sort also. So in merge sort, what happened actually, we have the first call tn, and we have the additional time n for merge process. Okay, this is the first, and after that we have two call t n by 2 and t n by 2. Okay, and here we have two call, and size is also divided by 2. So that means number of operation required for merge part is n by 2 at this call and n by 2 at this call. Okay, and if you add this total n by 2 plus n by 2, because this is the call and this is the operations, so n by 2 plus n by 2, you will get n. Okay, again at the next level you divide this problem again, so you will get a total number of operation n by 4 here, n by 4 here, n by 4 here, n by 4 here. Okay, and when you add all these, you will get n. So that means each level you are getting the same number of operations, and total levels are log n. So that means each level you have n operation, levels are log n, so total complexity are n log n for merge sort. Same for quick sort, but here we are getting the different things. So here we are getting this number of operations are increasing at each level, so we cannot directly use this formula. Okay, and you will also get sometimes when the number of operation will decrease at each level. So like binary search. Okay, like binary search, you have the tn first time and the plus constant time here. Okay, so no, not binary search example is correct. Yeah, but in this week we are learning one quick select algorithms. So in that case you will find out that, so that the recurrence relation is like that. So t n equal to t n by 2 and plus n. Okay, like this you will get a recurrence relation like this. And here if you solve this recurrence relation, so you have t n and number of operations are required n at the first level. When you call two times, so t n by 2, no, here we are not calling. Okay, so sorry, only one time call. So here one call is there, so t n by 2, so that means input is n by 2, so your number of operation will also reduce n by 2.
Sir,
Next call
sir,
t n. Yes.
may I ask one? Just you came so quickly here. In the previous one, while calling it, why they are also calling with the number 4? It is a 4-digit number both. So why 4 is past the previous one? The little scroll up, little please. Yeah, there. Line number 17. Line number 17 there in the code.
Yeah, this 4 is for what is the size of this number? How many digits are there?
Okay, and
this is the length of the number actually, number of digits.
And the multiplication is happening at the 2-digit level or at atomic level, like 1 digit?
No, you will finally, when you call this function, you will get a complete solution. Okay, you will get a complete solution. This is the correct solution for this calculation. When you multiply this 3, 4, 5, 6 into 8, 9, 0, 2, you will get this number. But how we are doing this multiplication? We are not directly multiplying 3, 4, 5, 2 or 8, 9, 0, 2. So internally, the multiplication also perform stepwise. Okay, So that stepwise in naive approach, you have seen that we perform like this operation. So you have suppose 1, 2, 3, and 1, 1, 1. So you perform like this 3, 2, 1. You first multiply this number with all numbers. Then after that, you perform like another 3, 2, 1. Then another next is 3, 2, 1. Okay, and then after that you perform add operation. So that 3 and 5 and this 6 and then 3 and like this. Okay, 1. So this multiplication perform internally in some step by step. So how we can reduce this time actually? Okay, so how we can reduce this multiplication time if you are performing any large multiplication? So this is the naive approach to perform multiplication. So that takes order of n square. So what is the n means here? Here input size n, we are considering that the number of digits in the number, and we are also assuming that we have the similar digit in the both number. Okay, so this is also a one assumption for this algorithm. So we are passing the same digit length for the x and y, and that is actually given as a n. So here n is defined as a size of the digits. Okay, and this is the input for this. And after that, we are breaking this problem. We are breaking the that input number size into the half. So the 3, 4, 5, 6 will divide into two different values, 3, 4, and 5, 6. And same 8, 9, 0, 2 will be divided into two different values, 8, 9, and 0, 2 separately. And after dividing this way, we are calling the function recursively, and again it will divide. So this after getting 3, 4 in the new call, so 3, 4, and this 5, 6. Suppose here 3, 4 x is 3, 4 and y is 5, 6. Again it will divide next. So x will become 3 and then y will become 4 like this. Okay, and once if you are getting n equal to 1, so this is the base case of recursive call. Okay, so that means you are reducing the size, you are reducing the your digit size, and when it reach at the 1, you will directly return the multiplication, x into y. So that means this one single digit multiplication you can directly perform. Okay, here our
But
problem
sir,
is
we are
yes,
not doing it half, no? We are dividing it and multiplying it by 10. So it's not half, right?
no, this is half actually.
It's not.
You can see this calculation, you can see this calculation, what it is doing, it
It's
is returning the half value.
okay.
This is not a multiplication, this is a power 10 to the power m.
Okay, okay, okay.
Okay, so that means we are dividing x value by float division by 100. So 10 to the power 2 we are getting for this digit. So this is float division, that means you will get a integer part only after dividing by 100. So you get
Thank
40.
you, sir.
Okay, this will return a reminder. So last two digit. So in this way your digits are breaks actually into the half part. And
But sir, if it is an odd number, how will it work? Because this is 4
yeah,
digits, so it can.
it will work because here we are performing some that division process. So that means if we are getting 5 digit number, so this will perform like 5 divided by 2. So you will get a first digit, you will get a 2 and another by 3 size.
Okay, okay.
Okay, yeah. So in this way we are breaking this problem and we will get some another. Okay, so here regarding the complexity, here each level our that number of operations are increasing. Okay, so these are some case when we calculate the number of operation at each level. So maybe you will get a same number of operation at each level. Sometimes you will get a number of operations are increasing. Sometimes you will get a number of operations are decreasing. Okay, in the each level. So based on that, we will decide our complexity. So that actually discussed in the last topic, recursion tree. So how we can decide, and we that giving some direct formula. If you're getting this type of patterns, you can directly use that formula to calculate the complexity. So that I'll come that. Okay, so quick select. Okay, first thing this. Okay, so next algorithm is so I'll calculate the complexity of each after covering this all topics first. Okay, so this is next quick select and fast select. There is one more algorithm I think left, that is Oh, that is missed here. Oh, we missed this here, this closest pair point. Okay. So this is one more algorithm which is discussed. So closest pair of points. So this is also a one that very common real life scenario based example. So that you have to like 2D or 2D surface and some points are given at that point. Okay, like this. So a number of points are there. Now you want to find out that closest pair of points. So the 2 points which are actually the closest in all the combination. So among all the points, which 2 points are actually the closest point? So we want to figure out this. So, and this information is required too much used in the gaming actually. So like if you're just performing some gaming, so what are the closest object to you? So some indication that you will get if any object is closer to you. So how this information is calculated when you have multiple object in 2D surface like. So this algorithm is also important. So if you have this called 2D type of surface and you have n number of points, and then how you can find out the closest pair of points. So one naive approach you can try is you can take the point and for the remaining, so you can take 1 point and check the distance for all remaining n-1 points. Okay, that means you will get the distance of all the pair with 1, this first point, okay, with the n-1. Then you can pick second point and do the same process with the another remaining n-1 points. In this way you will get all the combination of the each point, so that become a n square complexity. So that means you are comparing 1 point to the another n-1, then second point with another n-1 like this. So that means n into n process. Okay, so this is the one naive approach how you can improve this. So that algorithm is closest pair of points. So same approach we can apply here, divide and conquer approach. So you can see that professor will also discuss this on that gaming example that is used, and here some constraints are assumption is also given here. So like this condition, so assume no 2 points have same x or y coordinate. So that means in this coordinate we are assuming that 2 points are not coming at the same that x coordinate or y coordinate. All points are randomly exist in the same different positions, but this condition is required for this algorithm. Okay, so if we have this fulfilled, now we can apply this divide and conquer approach. So how this approach is work? So let's take the slides. This one. So here actually, yeah, you know that you can calculate the difference between 2 points. Here we have the coordinates of the each point in the x and y form, and this is the formula to calculate the distance between 2 points. Okay, so P1 is this and P2 is this. You can directly apply this formula and you can calculate the distance between 2 points. So this formula we can directly use, and this is the problem statement it is given. So now this is, yeah, this is one dimensional. Yeah, so here this is discussed. So dividing the points. So one dimension, it is we can simply sort the point and we can perform sort the point and perform these things. So this is regarding the yeah, so we can sort the points. So sorting takes n log n time. After that we can figure out. So this problem we have already discussed in the week 1 or week 2 assignment problem. So where we have some numbers and we want to find out the closest to that pairs like this. So we can sort the elements and we can figure out the which elements have the minimum difference by just linear process. So, but in 2-dimensional, how we can improve this? So this n square to less complexity. So this is now similar we can use the divide and conquer approach. So first things, we will divide our area, actually points area, into two equal half, vertical half. Okay, so recursively compute closest pair in each half. Compare shortest distance in each half to shortest distance across the dividing line. So this is the next step. And what is the meaning of this? So what we are doing, actually, we have this region P, okay, where we have this all points are distributed. And after that, we will divide this area by two equal half, Q and R. Okay, we will divide this area till some point, and we will directly return the answer by that distance formula. Okay, so this is not a only one division. We will divide this problem multiple times recursively, and we will reach at the base case, and at the base case we will directly return the formula in constant time by that distance. So now this is the example to understand at this level. So suppose we have divided this problem into half part, and our final goal is to find out two points which are actually closest point. So what we can do, we after dividing this point, we can find out the solution for this half. Okay, so that means the smallest distance d1 between 2 points. Same things, we can find out the smallest distance between 2 points in this second half, okay, d2. So this is the 2 half. And also we will figure out that, because that 2 points can also be comes that across this line, divide line. So maybe you will get an answer between these 2 points, like, okay, so one point coming in the Q side and another point is coming to the R side, and this is the shortest distance among all. So this is also a possible area where you need to check. Apart from this left part separately, right part separately, you also need to check the border line also. Okay, so the points which are coming closer to the border line, we also need to check that points. So these are the three areas we need to check. So that means we will find out the shortest distance on that closest point in the left, that Q area, right area, and the border area. Suppose this is D3. You find these 3 points, you find out the closest point. After that, you will return a minimum of this D1 and D2 and D3. This. Okay. So this is the final things. We are dividing the problem. We are solving the each problem separately. So that means left part, R part, and we will also find out this border part. Okay, and then we will get, after getting the solution of all these 3 parts, we will return this minimum value. So that will be the closest point. So now this is the things. Now how we can divide these points, because here we have to divide this point in some different way, because this is the 2D area actually. Okay, so we will divide vertically, that this is the X and this is the Y. That means we are breaking that area by the X half. Okay, so there is some value for X, that some value is coming on this side, some is right side. So that process we will do. So here you can see, after doing this process, so this is discussed here, sir, that dq is the shortest point on this side, dr is the shortest point on this side, and after that we will also figure out some border area. Okay, so that border area and points which are coming in this border area, we will also check for this. Okay, so then we will figure out the shortest distance for so in this way, and after that we will return a final smallest point. So this is the basic idea. Now what algorithms does actually. So here I'm just giving the code explanation, so that this is the algorithm. Okay, so if our length of the points, okay, so if we have our points px, okay, so here what points are, so what is this px and py? So this is also important. So px, our points are arranged in to the sorted order of the x coordinates. Okay, all points. So we have the all points. So let's discuss this example. So suppose these are the points PTS, these are the points we have list. Okay, let's list of points. Now when we call this mean distance PTS, so that means how we start. So this is the main function. So we pass this main list, but after that what we are doing? We are sorting this list, sorted points. So sorted points is happening on the based on this X actually. That means this is the X and this is the Y axis. So our list will be sorted based on the first value. So this Px is referring to this all points, but sorted in based on the first coordinate X. Okay, so that is representing the Px. Now Py is representing the points which are sorted based on the Y value in increasing order. Okay, so this is the Py value. Points are same, but we have arranged our point into the sorted order. So Px and Py. And then we are passing this to our algorithm when distance are recursive. Okay, Px, Py. And this is the round of value actually we are passing. So now this is the main function. And our algorithm actually, you can see this is the base. This is the base area actually. No, this is the formula to calculate the distance. So this is the formula directly. And this is the main call. And first we are calculating that S equal to len of Px, because len of Px and Py are the same. So we can calculate the length by any list, Px or Py. So here, if S equal to 2, so that means we have only 2 points, Px0, Px1. So we can directly return the distance between 2 points by this formula. Okay, so this is a constant operation. We are assuming this as a base case. And also, if we are getting 3 points, then we can also get the shortest distance. So this is the first call, P0 to P1, P1 to P2, and P0 to P2, and minimum among all these. So that means we are making the base case if our point length of the input is 2 or 3. Okay, if our length is 1, so that means no points are there, so we can directly return 0 for that. So that will not come in this case. So here this is the base case. If our length of that list is greater than this, so what we will do? We are dividing the points. So for more than 3 points, divide the points Y point around median of X coordinate. So X coordinate. So here we are dividing the points with respect to X or midpoint, actually median of X. So we are just finding out this M equal to S divided by 2, so length by 2. And then we are figuring out that because our list is sorted, okay, so this Px is sorted. So we are picking what is the middle elements, so that elements. And we are just considering that the first element which are coming from this middle element are Qx and this is Rx. Okay, and this XR is actually, we are considering that this is the minimum value of Rx. So this is the middle point actually. We are considering the Rx 00. So this is the middle point which are coming on the border. So that we are considering that XR. So in this way, we are dividing the points like this. Here is the comparison. Yeah. So this is the area happening. So first thing we have all the points. So we are figuring out that so all points are sorted. Suppose if you just look from this side, all points are this is coming first, this is coming second, third, like this. So you will get all points. So among all the points, you are picking the middle point and you are just separating the points. This is coming in the Q and this is coming in the R. So in this way, we are dividing the problem in the code and you are getting this new. Actually, this construct Qy, Ry in order of n rather than Py, from Py. So we have divided this like this. And same things we will do with that Y based on the Y coordinate. So we will also separate all the elements based on the Y coordinate. qy ry. So by looking this loop, we are just appending all the points in qy area and ry area. So one second, yeah. Okay, so the points which are also looking like this, so all this like, so first we are dividing like this, and we are also dividing in this direction also. Okay, so we are just shifting this, you can see qy ry. Okay, so that was divided based on the x coordinate, but now that we are dividing by the y coordinate also. So construct qy and ry in the rather than from py. So we are reading all the element and looking that if our p0 value is less than xr. So this xr we have decided at this point. If it is lesser, then we will append into qy dot append p, otherwise ry area. So after dividing this process, now we are calling this function recursively. Here you can see we are applying the recursive call. So delta, this min of, this is the left part call. Okay, so min distance of left part x, qx, qy. Okay, so this list is sorted based on the qx, and this is based on the qy. Okay, and similarly we apply the same process on this side. So after dividing of the half, now this qy is representing the sorted order on this half, and that ry is representing sorted order in this half. So because of that, we are calling the same algorithm on the both this left part and r part, and minimum among all these. Okay, so this is the first call. And apart from this delta, so delta is representing the minimum among all this left half or right half, but we need a border area in also. So because of that, we are doing this process. So sy, this points we are actually using for the border area. So here this is the main actually part of this algorithms. So what area we need to find out. So after getting this delta value, in the this part, so suppose if you have received dq and dr on the right side, and delta is representing minimum among this left point and left closest point or right closest point. So this is the closest point among all these two sides. Now we will only look, so from the border, this border part, we will only look the area, only this, that delta on the left and delta to the right. This area we will only look, because if any points are coming out of this, so you will not a shortest, that closest distance for that. So if any points are coming in this area like this and this, then there is a chance you will get a closest distance compared to this delta. Okay, so because of that, we are only looking delta, this delta value on to the left or delta to the right side. So this area we will only check, and in this area what points are coming, actually what points are coming, we will calculate the distance for only those points. We will not check for the remaining points. So that means this side points we are calculating separately, this side we are calculating separately, and now in the middle part only this delta and delta, left delta part and right delta part, this region we will look, and we will compare the distance among all these points. And also we will not compare the points which are coming like this is the lowest and this is the toppest. We will not compare these points. Okay, and next part is discuss that what area actually we need to check. So here, according to the algorithms, so this is created, so corresponding to the border line, so we are looking the delta side, this delta side on the right, okay, left and right. And also we are dividing into this in different sectors. So you can see each cell we have divided by this delta by 2 square area. So here you can see delta by 2 like this. So that means you need to check only this 16 area to find out the closest point. So that means if any points are coming out of this 16, no need to compare which are coming to the border. So you need to compare this point with only this 16 blocks. points which are coming inside this 16 blocks, you need to compare corresponding to that points only, not all the points. Why we are doing this? To reduce the time of this process. Otherwise, what happens, suppose if all endpoints are coming to closure this, okay, all endpoints are coming closer to this border, then what will happen if we compare all the points with corresponding to the all remaining points which are coming in this border? So it will become a order of n square complexity. Okay, so n into n. Then we don't want to this. So what we want to this? So here what we are doing, we are just finding out the closest distance of one point with corresponding to the 15 points maximum. Okay, so 15 points which are coming on these 16 blocks. Okay, so then one point will compare with 15. So this 15 is now constant value. Okay, so if you compare n points or any number of points with 15, so it will become a 15n. So still it will remain a order of n. Okay, so here we are using some constant points to compare the distance. So that is our final goal here. Actually, we want to fix this comparison on the borderline with this constant number of points, and also no need to check the point, because if you see this area actually is a delta. If you comes to this point, this also a delta. If any points are coming lower this and above this, that means definitely you will get a more distance, and you have already figured out the delta distance as a minimum distance among left and right. So no need for the higher distance point to check. So because of that, if any points are coming at this point, so you need to check the distance all this maximum this area. Okay, so maybe another point is coming this part. Okay, and your point is coming at this, or maybe another point is coming, so which is actually lesser than delta. So that is actually the useful. So during this process, only compare with this next 16 points. So that we are doing in the process. So in the next part of the algorithm, yeah, this part. So we are finding out this ASY list, that points which are coming on the border within this length. Okay, so this delta, this we have figured out delta, and we are finding this XR is the border point. Okay, border, and we are figuring out all the points distance between this XR. If this distance P0 minus XR is less than delta, so that points you will consider to check in this SY list. Okay, so we are figuring out all the points which are coming in this border within this length, and after that we are performing this task. So you can see size, this is the size for SY, and here you can see what loop we are running. So this first loop we are running for the all points which we have taken in SY list, and second loop you can see we are running to minimum this I plus 15. Okay, so any point is coming, so we have sorted the point in to this border. Okay, so the first point is coming like this. Okay, like this. So if we are taking this first point, we will only compare that to the next 15 points only. Okay, so that I equal to minimum I plus 15, or size minus. If suppose we don't have the next 15 elements, so we will take this size of S minus 1. So we will compare each point with next 15 points. So this part actually become a 15 into size of the S1. So this, suppose this is n, so n. The total complexity of this part become order of n. This is the constant value. So now you can see this part is now constant big O of n. Okay, and so if you see the we are calling this function recursively 2 times. Okay, of the half size, we divided the point into the half. So now this is the 2 recursive call. Apart from that, we have all the that this is also a order of n time operation, p in py, and all operations are order of n actually. Okay, so if you see this, so this is a constant operation for distance calculation. Now if you see the complete algorithms, you have 2 recursive call. So the Tn and two recursive call 2Tn by 2. Apart from that, all operations are order of n. So overall operation is n. Okay, so Tn, 2Tn by 2 and n. So two recursive call, other operations are performing in order of n time. Okay, you will not get any operation of the more than order of n complexity. So because of that, yes.
Like solving this 2Tn by 2, generally when we have a 2 times recursion call, it goes in the complexity of 2 to the power n, right?
No.
Okay.
This 2, you are saying this 2Tn by 2?
Correct. How
yeah,
how
one?
do we solve that complexity to arrive at the complex? I mean, how do we solve this recurrence to get the complexity?
Okay. So this, actually I have explained this. So this recurrence relation. So that means I'm explaining new page. So suppose if you have Tn equal to 2 recursive call of n by 2 size plus n. Okay, this is the recurrence relation. If suppose if we expand this with the help of tree, so that means first call is Tn. Okay, now we have two call Tn by 2, Tn by 2, correct? This is the two call I have written this. Okay, plus we have n time, correct? This. Now this is the new problem. This is the new problem. Okay, if you have input size n, you need n operation. If now the new problem Tn by 2, that means you will write like this, so 2Tn by 4. Okay, so you just replace this n by 2 at every place in this equation. So it will become a n by 2 like this. Okay, I've just replaced n by 2. Just replace all this place. So you will get this equation. So here what we will do for this problem, this is a sub problem. So that means we need n by 2 operation. Okay, so that means if we expand this, so that is two recursive call again. So Tn by 4, Tn by 4. Okay, so that 2, and apart from that we need the time is n by plus n by 2. Okay, two recursive call and plus n by 2 time. Same here, Tn by 4 and Tn by 4, and additional time is required n by 2. Okay, so now at this level you need n operation. Now next level, n by 2 plus n by 2, you need n operation, correct? N by 2 plus n by 2, 2n by 2 equal to n. And so this is the next level. Now this is the third level. So here n by 4 plus n by 4 plus n by 4 plus n by 4, you will get a total 4n by 4. That means n. Okay, in this way you will get at each level total n operation are performing. And now how many levels are required? You are starting from n. If you are starting from n, next time is n by 2, next time is n by 4, next time is n by 8, and till 1. So how many steps are there? So these are log n steps actually. Okay, so in log n steps you will reach this one. So here total levels are also log n. Okay, levels are also log n, and each levels n operations are required. So log n levels are there, each level n operations are required, so total n log n. Okay, so we are getting this n log n for this type of relations. When we are getting the same number of operations, we can directly multiply with the operation into total number of levels.
See, I understood that n log n for the n part. I didn't understand that complexity for Tn by 2 when we keep splitting it down. How do we, what happens to that? That happens to become 1?
So actually this is a call. This is a recursive call. So what happened when we just expand this more? So at last you will reach at a T1, correct? So n by 2, n by 4. In last you will reach at a T1. And for
Right.
T1, actually if we are getting single element, so we will not do anything. So that means this operation is a constant operation, 1. After that, it will not expand. So this is the base case of the algorithm actually.
Yes.
So at this level, also you will get a total number of n operations. So last level, that means you will have a total n times T1 operation. Okay,
Correct.
so in merge sort also you've seen that if you have suppose 8 element initially, okay, 1, 2, 3, 4, 5, 6, 7, 8, like, okay, then next time you will get a 4 elements. Next time you will get a 2 element, okay, and last time you have a on single element. So now when you're getting the single element, so this is single element. That means if you want to sort this part, no need to sort, directly return this. Okay. From here, you can directly return this. So this is a base case. Each recursive algorithms have some base case when we stop the recursive call. So that base case is actually a constant operation. And at that time, we just perform that constant operation in unit time. So this means this is a constant operation. So 1, 1, 1, 1, 1, 1, 1, 1. Total 8 elements are there. So total 8 operations are required here. So 8n. This is equal to n. After that, you will merge this process. So merge one like this. So merging these 2 elements need 2 times comparison. This 2 times, 2 times, 2 times. Total 8 operations are required. Then merging these 2 elements separately, it takes 4 times, 4 times. 8 operations are required at this point. Okay. Now merging this 4 element, it will take total 8 operations, 8 comparison. So every time you can see you are getting total number of operations at each level are same. So we can see that total log n steps are there and log n and multiply by this number of operations. So n.
Okay, so 8n into n log n, basically log n. Yeah.
Yes. Okay. So in this way, we are calculating this. So because we draw this recursion tree for the recurrence relation, where this actually tree branch is represented the calls actually. Okay. This recursive calls. Not this.
So in recursion, sometimes it goes into 2 to the power n. When does that happen?
So that happens like this. Suppose, yeah. Suppose your algorithm is working like this. So you have some fn function. Inside that function, you are have some base case, and after that recursive part, you have called like this: fn minus 1 plus fn minus 1. Okay. Here we are not dividing the problem into half. We are reducing by 1. So that means the recurrence relation will work like this: Tn equal to 2Tn minus 1. Okay. And plus that one constant time. Okay, that operation. So what happening if you draw this tree? So that how this is expanding actually. So this is now Tn, then 2 call. Okay, Tn minus n minus 1 and Tn minus 1. Okay. Now next part, it will again Tn minus 2, Tn minus 2, Tn minus 2, and Tn minus 2. Okay, in this way, it will expand till nth level. Okay, so this is 1 level, this is 2nd level, this is 3rd level, and it will expand till nth level. Okay, it is not here this time levels are n, not log n, because our problems are not dividing by 2. It is just reducing by 1. So if you count the operations, so that one operation for this level, here 2 calls are there. So constant 1 plus 1 and plus 1, it becomes 2. Here 4 calls are there. So total 4 operations are there. So 4. Now next level, it will become 8. Okay. So it will become 8. So you can also write like this: 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. Okay. So this is 3rd level, 2 to the power 3. Okay. Now you reach at the nth level. So you will get a total 2 to the power n level. So that is the highest number of operations. So you will get a complexity this 2 to the power n.
Okay.
Okay. So if you are the tree is expanding till the nth level every time, if you are expanding that like 2 child, So you will get a 2 to the power n. If you're that you're dividing like this 3 child every time, so you will get a 3 to the power n in this way. Okay, so
Okay.
that depends on the level, how many levels we are dividing, and also each levels how many operations are performing. So this is the one thing. And okay, so this is closest pair. So just apply some one dry run on this. So I mentioned that each part explanation. So what we are doing here, we are dividing the points into left and right half, and in the left half also we are sorting the point into the based on the x coordinate and y coordinate. Then again calling the algorithm recursively on the half part. Same things we are doing with the right part. We are sorting the right points based on the x and y coordinate. Then we are calling again. And after getting this distance delta among left or right half, then we are finding out the border area. So we will just only cover the delta distance to the left and delta distance to the right of the border, and we will just consider that points. And also in that points also we will compare each point with the next 15 points only, because that is the possible area where we can get the smallest or closest point distance point. Okay, so because of that, this loop is actually becomes a constant linear loop. Okay, so 15 times n. So this is also order of n. So overall complexity become n for the remaining part of the calls. So apart from the calls, the remaining complexity of the part is order of n. So we will get the same that recurrence relation, and overall complexity will become order of n log n. Okay. So this is the one algorithm. This week we have many algorithms actually. Okay, so this is the fast select algorithm. So this is one more, and median of median algorithm. Okay, so next algorithm is quick select and fast select. What is this quick select and fast select? So meaning, so here meaning that quick select, we are searching some element. So what is the goal of this algorithm is find out the kth smallest element or kth largest element like this, and we have some unsorted list. Okay, so suppose we have like a 3 4 2 6 8 1 9 like this, some unsorted list, and we want to find it out that the third largest element, like, okay, so we want to find out third largest element. So to find out the third largest element, what is the procedure you can perform? So you can identify the first largest, then second largest. You can just do this process. Another way is you can sort the list. Okay, you can sort the list, and after sorting the list, you can find out the sort that third largest or fourth largest easily. Okay, so that takes at least n log n time. Okay, the very naive approach takes n squared times. Okay, after sorting, you can reduce to n log n time. But is there any way we can sort more? So that is actually the main part of this. So how we can find out this? So here, quick select, actually this is very closer to the quick sort. So what we will do, we will perform the same things. We will select the pivot element. So in pivot element, you know that what pivot position actually represent. So if you are performing, if you are taking this 3 as a pivot element, okay, and in partition process, suppose if you are looking the third largest element, or so third or second largest element, like the second largest element in this, and you apply a partition process, you take this as a pivot element, so you will perform a linear partition process. After that, you will get a third at the correct place, and all the remaining element will come before that, will be smaller than, so like 2 comma 1 like this, and remaining elements will come on the right, so like 4 6 8 9. Okay, no need to always, so this maybe not in sorted order, and same thing from this side. But here we can identify one thing. So that means if we find out that the what is the pivot position we are getting. So suppose pivot position we are getting 0 1 2 3 4 5 6. Okay, so here this is the indexing. If we are getting 2, so this means this is the third largest element, the third smallest element. Okay, third smallest element, we can confirm that. Okay, because this 3 is now come at the correct position, 2 index. 2 index means third position. So that means this is the third smallest element we can finally confirm after getting this information in linear time. So if we are looking to the second largest, so definitely the second largest will come to onto this left side. Okay, before this position. If we are looking for the fifth largest, smallest and fifth smallest, so fifth smallest will come onto this side, not this side. Okay, so based on this pivot position, we can decide that which area we need to check next. Okay, and we can discard the remaining area. So in this way, this problem is decreasing that of half of the size after every pivot that position, after getting the every pivot position, and we are reducing the size. So in this way, suppose if our algorithm is working in the best or average case, so that means we will divide our algorithm in each time half part. So that means what happen if we have n element, we will divide our part n by 2, n by 2. Okay, and we are only looking only half part. Based on the pivot position, we will discard one of the half part. So that means either we will discard left part or right part, or maybe sometimes we will directly get the correct position of the pivot and we will directly return the answer. Suppose we are looking the third smallest element and we are getting the pivot element at the third position, so we can return that answer. But the another case, we can discard half of the part and we can decide which part we need to check again. So in this case, we can discard like this. Okay, so we'll discard this and we will check on this if we are looking the large right side value. So here we are not performing two recursive call every time. So we will perform one recursive call with the half size. So this is the case for the best and average case. When we are getting this divide part actually from the half part. Okay, so what will be the recurrence for this type of algorithm is Tn equal to, now we will call the one half, call the same algorithm on one half, so that is actually Tn by 2. Okay, apart from that, time required for partition process, that is actually linear time, so order of n or n. So now this become a recurrence relation for that that quick select algorithm. Okay, now this is the basic same quick sort algorithm. Now we are just using that algorithms for the quick select to find out the kth smallest or like this lack of information. Okay, so you can see we are doing the same process. We are just finding out the pivot. After that, we are getting the this lower. This one is representing the pivot position, and after that we are deciding the call. You can see if our k is less than the lower limit, we are calling the one this recursive call. So based on if else condition, we are calling only one time. If our k is matched with the required things, so that we are returning the answer. Otherwise, either we are calling on the left part or right part based on that. Okay, so we will call only the one part. So because of that, our algorithm is working like a Tn equal to Tn by 2 plus n. Okay, and for this partition process above one. But the worst case, so similar to the quick sort worst case, if your pivot is coming at the one side. Okay, so if suppose if you are looking, so you have some element, and if you select this first element as a pivot element, after completion of the partition process, this pivot is coming at the one corner, either left or right. That means this is the pivot position, and remaining n minus 1 element, you need to perform the quick sort or quick select algorithm on the remaining part. So then this is the worst case. This become a order of n square complexity. So now this time recurrence relation will become Tn equal to Tn minus 1, because our pivot is coming first position, we will discard this position and we will work on the remaining part. So that right part is contains n minus 1 element. So that means we have to call the same algorithm on the right part with n minus 1 Tn. Okay, Apart from that, we are using this partition process n time. So now we are getting this type of scenario. So you will get a n plus n minus 1 plus n minus 2 this series, and you will get a n into n plus 1 overall order of n square. So this situation, whenever pivot always comes to the corner, either left or right, then it become a worst situation. At this time, our quick select algorithm also take order of n square. So no benefits for that. So how we can improve this? So this is the divide and conquer approach, but here this is the worst case situation we are getting for quick sort as well as the quick select. So now there is one more algorithm is discussed, this median of medians, the median of medians algorithm. So that means we want to find out a good pivot actually. We want to find out a good pivot, so that will not come to the corner point at least. Okay, it will come in between. So that means we are just improving our worst case situation for quick select as well as the quick sort with the help of this. So median of mediums, this algorithms actually provide a good pivot element in linear time. So because of that, we can just use this good pivot for our partition process, and we will improve our worst case situation. So how this median of medians algorithm works actually? So if we have list, suppose if we have n elements, okay, now what we will do, we will divide our all list into blocks of 5 element. Okay, so we have total n elements. Now we will divide our all elements into block of 5 elements like this. Okay, after that, in each block, each 5 blocks, we will figure out the middle element. No, each 5 blocks, first things we will sort the block. Okay, we will sort the block. Okay, and we will pick the middle element as the median of the each block. Okay, in this way you will get all middle element of each block, and after getting this middle elements, again you will do the same process. You will divide again into the same 5 block. If you are getting more than 5 elements, then again sort the block and then pick the middle elements. So in this way you will get a middle element finally. So like this, and this element definitely will not come into the corner point when you will use this element as a pivot element. So why? Because this is the things you are getting this sorted things. Okay, so blocks, and you are picking this element as a pivot element. Okay, so definitely these elements which are coming on this area, okay, this area, all these elements will be smaller than this blue elements. Okay, because you are picking the middle element, all the middle blocks. Okay, like this you are picking this. So and you are all these are into the sorted order, so definitely this area elements will be smaller than these elements. And similarly on this side, all these elements will be greater than this. We are not sure about this above part and this lower part, but still you can see some 1/3 part at least we are getting smaller, which are smaller than this. So that means this blue elements will not come onto the corner at any time. Okay, it may be come so like this range. So suppose if you have so here 5 and 2 3 4 5 6 7 8, so some 80 elements are there. So these number of elements are smaller, these number of elements are greater, and your elements come at the position in between, after 1/3 on the left and 1/3 on the right side. In between your element will come. Okay, this median element, if you are selecting this element as a median element, it will not come into the right corner or left corner. So we can, how this algorithms actually work in the code, you can see this implementation, and this is a linear implementation. We are doing this process in linearly. We are finding out this median in the linear time. Okay, so this you can see we are just looking that if len of the L is less than equal to 5, we will sort the list and return the middle element. Otherwise, we are just breaking our list into the mid that 5 blocks and sorting the blocks and for that appending the middle element into our that median list. Okay, and calling the same function recursively again, MOM. Okay, so first things we are just dividing each elements into the 5 blocks and sorting. So how this become works? So this is a, you can see range of 0 and len. We are traversing all n elements, but inside this is a fixed 5 constant operation, and this is also a 5 log 5 operation. Okay, 5 log 5. So this is also a constant operation. So this is constant, this is also constant, this is also constant. So that means this is the linear loop. Inside the linear n loop, we are performing all constant operations. So overall, this is a order of n operation. So because of that, overall complexity of this function becomes a order of n. And we are finding out a good pivot element with the help of this order of n complexity, and we will use this to select the pivot element in our fast select algorithm. Okay, so we will use the same quick select, that quick select or quick sort algorithm, but we will select the pivot element by this algorithm. So that this is the function, and inside this function we are calling this main function, and we are selecting this pivot element with the help of this MOM function. So it will return a good element which will not come to the corner, and you will get a good complexity like this. So your that recurrence relation will work like as a Tn equal to Tn by 2 plus that 1, sorry, n for partition. If you draw the recurrence relation for that, you will get a that Tn, and then next is Tn by 2, then next is Tn by 4 like this. Okay, so each level you have n operation, next is n by 2, next is n by 4. So this time you can see this is reducing at each level, this is reducing, and total log n steps are there. So these are the 3 cases we have. So this is the fast select algorithm, and here this algorithm will return a any largest element in order of n time. So this is the complexity for this type of recursion. Okay, so order of n. So now you can see recursion tree. So as we have discussed that when we are just expanding our tree, so we will get this type of situation. Either our number of operation at each level will be the constant, okay, same. It may be increasing, it may be decreasing. Okay, so 3 type of condition you will get at the each level. Now based on that, these conditions are defined here. You can see these 3 conditions, and we are considering this our recurrence relation like this. Okay, so Tn equal to this R is the number of call and C is the value of which we are dividing actually by the input and by C. Okay, so in this way, if the value is equal, then you can directly call the complexity Fn into log n. So what Fn value is, suppose if you have given like the Tn equal to that R, okay, and T, sorry, RT, and this is divided value. So this is n by C plus Fn. So this is the corresponding equation for recurrence relation. So R is the number of times we are calling this recursive call, C is the value which we are dividing by, and this is the function, what is the time which apart from this recursive call. So we will use these terms here. So if our number of operations are equal at each level, so that means you can directly put this complexity. So Fn, what is the value is given here, Fn into log n. Okay, if Fn, if this value is given n square, okay, then you can use the n square log n directly. Okay, so just use Fn or into log n if the number of operations are same at the each level, all terms in the series are equal. Okay, if the number of operations are each levels are decreasing, then you can directly write the complexity big O of Fn. Okay, so like previous case, we have seen that Tn equal to Tn by 2 plus order of n. Okay, so for this type of case, you can see number of operations are decreasing, n by 2, n by 4 at each level. These are decreasing. So what is the value for Fn is n. So we will consider this as a overall complexity for when our number of operations are decreasing at every point. Okay, by some fact, that constant factor. And if our number of operations are increasing, okay, series grows exponentially, each terms a constant factor larger than the previous terms. So like that Karasuba algorithm, we have seen that. Okay, so that algorithms that we have discussed, that that was the Tn equal to 3 Tn by 2 plus n. So this 3 will be work as a that R, and this 2 will work as a C, and this is a Fn. If you draw the tree for this, so you will get a the Tn, and this will expand 3 times. So 3 the Tn by 2, Tn by 2 like this, and same for here Tn by 2. So that means here number of operations are n, but here n plus 2, n by 2, n by 2, n by 2, total 3n by 2. Next level. Okay, so now it is increased. Actually, next level you will find out that 9n by 4. So that means it is increased by this factor. So you can see next level we are getting 3 by 2 ka whole square. Okay, by n. So your number of operations are increasing by this factor. So in this case, use this formula for the complexity. Tn equal to big O n to the power log base C and R. Okay, so this formula. So here we will put this value. So n log. So log is there, and C value we have for 2. Okay, so this log 2. R value we have 3. So this R become 3. This. So our complexity for Karasuba is become big O of n log 2 base 3. So this value actually we are getting 1.59 something. So this is n to the power 1.59. So you can just remember these 3 points after expanding the tree. First you need to just expand make the tree and figure out that number of operations at each level. Just figure out the pattern. The number of operations are same, increasing or decreasing. And based on that 3 condition, you can directly calculate this complexity. For same, if decreasing, just directly write the Fn complexity. If it is equal, use this Fn into log n. What Fn value is given in your recurrence relation, just multiply with log n. Increasing case, just use this n to the power log Cr. And also remember that what is this C and R actually in the recurrence relation. So in this way, you can represent the complexity for recurrence relation or recursive solution. Okay. Yeah, so these are the points. So you can remember these 3 points, so you can solve the complexity for recurrence relation. So this peak is little heavy, so I hope if you have any query you can ask.
Sir, before the exam, whether one more week will be covered?
So week 9 will cover in the next week, no? Okay, next week. Okay, so next week we will conduct maybe revision session. That 1 week before the exam, so that maybe 2 revision session. So actually we don't have any content in week 10. So maybe you will get some time for week 9 in the week 10. Okay. So we will take the session in the next week after the quiz for week 9. Okay.
Okay.
Yeah. Okay. Any query, anyone? Or Just you can also watch the video content and just check if all topics are clear. Otherwise, we will discuss these things again in the revision session before the quiz.
Sir, for the OPP, any special attention to be given to any particular topic side or?
Yeah, so generally we release the mock also, but you can focus on the one problems directly from the graph algorithms. One problems before that, like linked list or that binary search topics. One problem from the dynamic programming, or one remaining problem from any another topics. Okay, like these are the area you can focus more. Okay, we will discuss this after the quiz.
Okay.
Yeah.
Sir,
Okay.
can I ask some questions in the next session about this week?
The next session is Friday session, so that is coding session. But yeah, next week we will conduct revision session for 2 weeks. At that time, you can just collect the questions and you can ask. Okay.
Okay, sir. Thank you.
Okay. Okay. Then if there is no question, no query, then we can close. Okay. Then thanks everyone. Bye.
Thank you.